All right, for our Arduino experiment, we set up an experiment with a DC fan motor, a DHT motion/temperature sensor, and our goal was to increase the fan speed when the sensor senses an increase in temperature. So this experiment was designed to increase the speed of a small fan attached to a DC motor when the system senses an increase in temperature. When I say system, I mean the DHT11 temperature sensor. The main task of the Arduino program is as the sensor senses an increase in temperature, the DC motor will be fed more voltage, and meaning an increase in RPM, the fan speed. The conclusions drawn from this experiment is that a clear relationship between the increase in temperature and the increase in motor speed does indeed exist, and that data gathered from the experiment will provide useful for future experiments. Moving on to the instrumentation section, the parts required for this experiment involves an Arduino Uno or Mega 2560, Arduino IDE application, several wires, 220K resistor, diode, a transistor, a DHT11 temperature and humidity sensor, along with a DHT motor attached to a small fan. The wire setup involved the DC motor and temperature sensor must be done correctly before the Arduino program can run, such like a MATLAB program, it's not going to run correctly or it might take longer to run. And the Arduino IDE program will display the temperature, humidity, and the fan speed when the program is being ran. So moving on to the wire setup, pictured on the right at the very top is going to be the DC motor with the positive and negative wires. The diode with the white strip on it is the top. The N is the transistor, and the resistor is shown with the 3 bands. You can see where the wires go on the breadboard and where the other wires connect to the Arduino. What is not shown on the right, is shown on the left, is the humidity sensor. The yellow wire is going to be the 3.3 voltage, which we found was sufficient enough to run the sensor. The white wire is the analog A0 connected to the Arduino, and the orange goes to the ground. Moving on to the procedure section, after setting up the wire and checking for errors on the Arduino IDE program, we run the program, and while the program is being ran, the data that is displayed should be the fan speed, the temperature, and the humidity. What we're going to use for our analyzation and the graphs, we're just going to use the fan speed and the temperature. All right, so this is a video of our system being ran, the hot wires being plugged into the breadboard, the fan is started to run. There's a hot towel come in contact with the DHT sensor. In the video, you can hear the DHT motor putting out more power. You can hear the fan starting to go a little faster. As you can see, you'll see that in the results section as well. So you see our little setup, fan needs some space to run. That's our experiment. I'm going to pass the torch to my friend Tyler.
The theory behind our device is it's a temperature-controlled DC motor cooling fan. The microprocessor of the Arduino is programmed to supply power to the DC motor when the DHT11 temperature and humidity sensor records a temperature within the range of 15 to 34 degrees Celsius. The DHT11 transducer measures temperature by using a negative temperature coefficient thermistor that decreases in resistance with an increase in temperature. This relationship between the temperature and the resistance is expressed by these 2 equations. The recorded temperature is then logged onto the Arduino interface, and when the lower temperature limit is reached, a PWM value is sent to the analog header of the Arduino device, which signals to the Arduino to supply a certain amount of voltage and current to the breadboard. The current and voltage sent to the breadboard then increases linearly until the upper temperature limit is reached. The linear relationship is expressed by these 2 empirically derived equations for voltage and current. The rate at which the voltage and current increases for every increase in temperature of 1 degree Celsius, there is a 0.01 volt and 0.02 amp increase. When multiplied together, the current and voltage sent to the breadboard generate power, as shown by the power equation below. The generated power is then amplified by the transistor and sent to the DC motor, which then rotates the fan. As the temperature increases, the power supplied to the DC motor increases, resulting in a linear increase in rotational speed, as expressed by the empirically derived equation below. The rate at which the rotational speed increases is for every 0.002 watts of power supplied, the rotational speed of the fan increases by 1 RPM. Utilizing the previous 5 equations, our team hypothesized that the rate at which the rotational speed of the motor increases with increasing power supplied should be perfectly linear. Now I'm going to pass it off to Logan to discuss the final results and analysis.
Hello. So the results of our experiment showed that our Arduino circuit did what we wanted what we wanted it to do. The speed of the DC motor did indeed increase as the temperature sensed by the DHT11 sensor increased. This slide shows our data in the form of a numerical chart and a graphic chart. A simple linear regression analysis was done on the graph to find the approximate function between the two variables. As our team wanted, there was an approximate increase of 10 rotations per minute for every 1 degree Celsius increase in temperature. As can also be seen from the graph, there's a strong linear correlation that exists. However, the relationship between the temperature and the speed was not perfectly linear. Our group believes this may have to do with the powers that is supplied to the motor. As stated before, the relationship between the power and the speed should be constant. Below is our theoretical chart again and our experimental chart. Our experimental graph shows that the slope between each data point of the speed changes seemingly at random. So possible sources of error that we guessed, there may have been some systematic error regarding the change in temperature that was done, or the fact that the environment changed constantly since we brought the circuit into multiple locations and we're at different locations ourselves. It's also possible that there was large amounts of gross error involving the user, given that our circuit is a bit of a mess in wires, and it's possible we didn't record the data properly. Another possibility is just faulty equipment. If one thing from the circuit didn't work properly, it could have affected the results altogether. What's also likely is just a random error that involved fluctuation in the electrical equipment. On top of the error analysis, we also did an uncertainty analysis as well. To find the uncertainty of our speed at each data point, we used the standard perturbation analysis. The uncertainty of the DHT sensor was found on the Arduino website to be about plus or minus 2 degrees Celsius. With that uncertainty and the equations for voltage and current that were mentioned earlier, we were able to find the uncertainties for voltage and current respectively. With the voltage and current uncertainties, we were able to then find a list of speed uncertainties. So this slide shows the uncertainty data in the form of a percent at each data point. As can be seen, there is a clear negative exponential-like shape. This could mean that there was more error at the beginning of the cycle when the system was starting up. So to conclude with potential applications or improvements, it's possible that we should have had a larger wire connecting the sensor to the circuit so that the temperature with the hot rag we applied to the sensor wouldn't affect the circuit altogether. We also should have had the circuit done in a constant environment. That also would have eliminated some environmental error or systematic error, if any. It's also possible we could have found a way to cool the motor and prevent it from overheating, as it's possible that overheating could have led to inaccurate results. We also should have had maybe a few more measurements of voltage, current, and power with all three of us, but on the same exact circuit. But it was hard for us to do that since we're separated. And it's also possible we could have used multiple power sources. We only used the USB power source. We could have maybe used a 9-volt battery or even more USB sources. But overall, those are our possible improvements. And that is the end of our presentation.